Great. So if you can't see my screen or hear me or anything like that, please just let me know in the chat. Although if you didn't hear that, then you can't put it in the chat. I'm here at the Oak Island Resort, so I'm in my hotel room right now. So if you're wondering why I have a unusual background and setting and so on, that's why. I sprung for the premium internet here, so hopefully the connection works okay. I tested it a little bit last night and it seemed okay. So why don't we get started? Plan for today's class, I want to finish Unit 3. Unit 3 is going to be the end of the material that's going to be covered next week on the oral test. So I'll send an email out probably sometime on the weekend with a bit maybe more clarity around the structure of what we're going to put. And I don't want to talk too much about it now just because it'll all be in the email. So that way everyone can see it and everyone will understand what's going on. If you have not yet booked a slot for your oral exam, please do so as soon as possible. I sent an email yesterday. I think 25 people still hadn't sent it. We're down to 17, so we're improving, but I'd like to see that number go right down to 0. Okay, so we're actually close to the end of Unit 3 already, and we spent last class talking about all of the different ways of all the considerations you need to be looking at when classifying acid strength for not just organic molecules, but any molecules. And we finished off with an example or two. This is just another example, which maybe we'll use to start off today's class. We have 4 different molecules here, and the first one there is called formic acid. You can see there's a slight difference in these 4 structures in terms of what atoms are here and what the structures are. So remember what we're supposed to be doing is we have a list of 5 criteria we use, and we consider each one of those in ranked order. So the first criterion is looking at the atom the hydrogen is attached to, and the further down the periodic table that atom is, the stronger the acid will be. We can't apply that rule here because we have all oxygens attached to hydrogen, so we all have the same atom in every one of these examples. Rule 2 is looking at the atom the hydrogen is attached to and the more electronegative. If they're in the same row, the more electronegative one will be the stronger acid. Again, it's all oxygens attached to hydrogen, so we can't really apply Rule 2 either. Rule 3 is looking for the possibility of resonance structures. If we're looking at hydrogens attached to the same type of atom, we look to see if any of the structures can have resonance structures. So just looking now, you've done a lot of practice, hopefully, with resonance structures and so on. I'm going to see if I can get this light on here. Maybe. Forget it. You're going to see my dark face. Out of these 4 structures, 1, 2, 3, 4, are any of these structures capable of making a resonance structure if you remove H+? So you can either turn on your mic and let me know. Yeah, okay, I see 1 and 3. 1, yeah. Both of you are right. So 1 can definitely, I don't know what happened just there, but hydrogen. Pencil, what are you doing? Hydrogen, carbon, oxygen, oxygen minus. So this has a resonance structure that looks like hydrogen. That looks terrible. I don't know what's going on with my pencil today. I think it's when I'm touching the screen with my hand. Anyway, compound 1 and compound 3 can have resonance structures. Therefore, compound 1 and compound 3 will be stronger acids than either of 2 or 4. So right away, we can kind of say that 1, 3 are going to be stronger. I'll just use greater than, I guess, 2 and 4. But now we can compare 1 and 3, and we would look to see which one of those might be stronger. And we can't really use the criterion of resonance structures to separate 1 and 3 because they both have 2 resonance structures. Now, one difference between these, though, is that number 3 has that CF3 group that's attached, and 1 does not. 1 just has a hydrogen. Do you think that CF3 is going to make this a stronger acid or a weaker acid? So will 3 be stronger or weaker than 1 with that CF3 group?
Stronger.
Anyone want to hazard a guess? Stronger. Good. Thanks, Katie. So 3 is stronger than 1 because that CF3 group has electronegative atoms. There's 3 of them. So when you take off H+, that anion will be stabilized by the electronegative atoms. Okay? So if you can stabilize negative charge of the conjugate base, you will have a stronger acid. So 3 is going to be the strongest acid, and I see this is increasing acidity, so 3 is going to be the one on the end, followed by 1. And in fact, looking at our possible answers, we're already kind of narrowed it down to D, but we'll continue looking at the other 2, 4, and 2. 4 will be a little stronger than 2 because 4 has an electronegative chlorine that could help stabilize the anion. The anion would look like this, Cl H2CO minus. So a nearby electronegative atom makes that a little stronger. So we would have then 4 and then 2. Cool. Okay, we're going to talk a little bit about bases. We talked a lot about acid strength. Organic compounds can also behave as bases, and you will see many examples in this course where we use organic molecules as bases. And you see the example I have here of a molecule of cocaine. Cocaine has in its structure that blue nitrogen in the middle. The nitrogen can act as a base. It can react with acids like, for example, HCl, and it'll make what you see on the right, which is called the hydrochloride salt. And this is a common thing that amines will do. Amines very commonly in organic molecules will act as bases, accept protons from proton donors, whether it's a molecule like cocaine or whether it's some other amino acid or other molecules in your body. This is quite common with nitrogen. So actually, if you buy cocaine, none of you should, but when cocaine is sold, it's actually sold as the hydrochloride salt on the right. And what some people do when they use it is they mix it with base. So you mix it with something like sodium bicarbonate. And if you mix them two together and heat them, you can convert it back to the free base form. So it's kind of sometimes called free basing. And the reason you might do that is because charged compounds, like the ones on the right, don't very easily cross membranes. Whereas neutral compounds, like the free base form on the left, much more easily cross membranes, and so people get a quicker high. It's quicker. Okay, we're going to see several other different functional groups now being used as bases in our course. We're going to see alcohols, which is the top reaction. In this case, the OH is accepting an H+. You need a strong acid to be able to use an alcohol as a base. It makes this guy on the right, which we call an oxonium ion. Don't worry, you don't have to remember that right now. You'll see it again. Alkenes, in the second example, they can also accept an H+ from a very strong acid. And you make things like this, which are called carbocations. Ketones can also accept H+ from very strong acids again, things like HBr, HCl. And you can make this kind of cation as well. We'll deal with those ones more in organic 2 for those taking organic 2. But many sort of organic functional groups that have electrons, right? They have electrons either in the form of lone pairs or in the form of pi bonds, because remember, pi bonds tend to be weak compared to sigma bonds. Those electron pairs can accept protons, and then you get these sort of high energy reactive structures you see on the right. It's going to form the basis of a lot of the chemistry we're going to be looking at in this course. Lewis acids and bases is another definition of acids and bases. Up to this point, we've only been using the Bronsted-Lowry definition, and that's the definition of an acid as a proton donor and a base as a proton acceptor. Lewis, who's the Lewis structure guy, he proposed that an acid could be anything that accepts a pair of electrons, and anything that donates a pair of electrons would be considered a base. And under this definition, Lewis acids and bases, every Bronsted-Lowry acid is still a Lewis acid, and every Bronsted-Lowry base is still a base. But a lot of other reactions that might not involve protons at all may also be classified as acids and bases. So the example that textbooks always seem to give is this one, where you have BF3 and NH3 reacting to make this complex, where the nitrogen donates a pair of electrons. It's a big juicy pair of electrons there on the nitrogen, and they get donated to the boron, and you get this kind of complex here. That's not an organic molecule, but Lewis acids and bases are very common in organic chemistry, but we give them a different name. If it's a Lewis base, we call them a nucleophile. Nucleophile just means it loves a nucleus. It loves positive charge. So a nucleophile is anything that would like to donate a pair of electrons to some region of partial or total positive charge. So in the example here, we have this high energy, it's called a carbocation, a carbon with a positive charge. And we have this base, which is cyanide, and it's acting as a nucleophile and attacking the Lewis acid here. And again, you make a molecule like this, you're making a carbon-carbon bond. We would call that a nucleophile in organic chemistry and an electrophile rather than Lewis acid and Lewis base. I just noticed some irony on this slide. Cyanide is the compound that killed Lewis. He died by inhalation of hydrogen cyanide. So it's not called a Lewis base because it killed him. It's called a Lewis base because it's donating a pair of electrons. Okay, so this is our definition. Electrophile loves electrons. Any word with phile on the end. Phile means to like or to love. So we just have some definitions here of nucleophile, electrophile. We'll use these a lot, starting, I think, in chapter 5, maybe 6. 5 or 6. One of those chapters, we're going to be using a lot of electrophiles and nucleophiles. We're also going to be using leaving groups. So this is when you have a compound where something leaves. So we give it a very descriptive name here. And we'll be looking at reactions involving electrophiles, nucleophiles, and leaving groups. So these are 3 good terms for me to introduce relatively early in the course. I'm noticing my slides. I'm advancing now. Okay, it's just being slow. Okay, nothing new on that slide anyway. Carbocations we're going to be looking at in more detail when we get deeper into this course. Remember when we did functional groups, how we can class alcohols as primary, secondary, or tertiary? And we did the same thing when we looked at alkyl halides, primary, secondary, or tertiary. For carbocations, we will be doing the same thing, where if you look at the carbon with the positive charge, the number of alkyl groups that are attached to that carbon will determine if it's primary, secondary, tertiary, or methyl if it has none. So in the example you see here, we have 3 different alkyl groups attached to the carbocation. This could be something like, I'm going to draw an example. My pencil's being weird today. Something like that would be considered a tertiary carbocation. And the reason for that is we have 3 different carbons attached to the positively charged carbon. Carbanions, we may be looking at, I think maybe unit 8. We come across carbanions. Carbanions are carbons with alkyl groups, but also a lone pair and a negative charge. Come on, slide, update. I paid for the premium internet, come on. Oh, there we go, we're back. Okay, so this is a carbanion. This is a carbon that has a lone pair and a negative charge. And these kinds of carbons are very reactive, both as bases. They would love to accept a hydrogen, a proton from some other source, and then become neutral. Or they can act as nucleophiles, which is a Lewis base. So these are very good bases as well. So you may see these later on in the course. Now, that's the end of Unit 3. Can you guys hear me okay, by the way? Like, is it okay quality other than this lag? Perfect. So what I'm planning to do then for the rest of the class is do some review, do some examples. Okay, voice quality is good, thanks. So what I'm planning to do, I have two things that I'd like to do for review. I have, first of all, midterm 1 from 2017. Some of the questions that are on this midterm are material that we haven't covered yet. I'll just skip them as we go. There's also another one here from spring 2016, midterm 1, which is a different kind of question on that one that I wanted to tackle with you as well. So I'm going to stop presenting and then start presenting again. Okay, looks like we're back. Come on, iPad. There we go. It's just a little bit of a lag here for some reason on the iPad. I think we're okay though. So this is the fall midterm from 2017. And I'd just like to go through a couple of different questions because a lot of the kind of question types that you guys will be responsible for will be present on this midterm as well. All right, let's do some of these more quickly. Neratinib is a drug that was approved by the FDA for the treatment of breast cancer in July 2017. Structure is shown below with 5 functional groups circled and labeled A to E. In the spaces, write the name of the functional groups corresponding to each letter. No, don't install anything, please. A. So you can see A. Okay, yeah, A. Whenever I touch the screen, it seems to do that. Let's get rid of some of that junk. Hopefully you can all see A. Thanks, Lisa. So A, you can see the nitrogen there. What is the name of that functional group? Amine, good. My writing's going to be worse because I'm doing my best not to touch the screen here. B, everyone can see B circled there. What do we got for B? Anybody? Alkene, great. C. There you go, Michael. Doing great. Amide. D is a nitrile. E is an ether. So just make sure that you can look at a molecule like this, pick out the functional groups and identify them in a question like this. Here's a related question. In the drawing of neratinib, I've pointed to 5 carbons with different letters, and I want you to give its hybridization. So in this case, if you look at A, we have a carbon that has a double bond and 2 single bonds. That means it has 3 electron groups, and a double bond counts, a single bond counts as well. So we have a total of 3, and that gives a hybridization of sp2. If you look at carbon B, same story, double bond, 2 single bonds, it's sp2 as well. C, again, sp2. D has a triple bond and a single bond. This carbon right here. Triple bond to nitrogen, single bond. That means it only has 2 electron groups to make its 4 bonds. And that's very good, Michaela. That's an sp. E, we have that carbon in between the oxygen and the ring. It has a single bond to oxygen, a single bond to the ring, and it's got 2 bonds not shown to hydrogen. sp3. If it's all single bonds, you're going to see sp3. I'm going to cross out that one because we haven't gotten there yet. Cross out that one, haven't gotten there yet. Question 3 says, which of the following molecules is not an isomer of the other 4? So what you'd want to do here is figure out what the molecular formula for each of these is. So for this first compound A, if you count the carbons, I count 1, 2, 3, 4, 5, 6. So that's a C6. H, there's going to be 3 on carbon 1, 1 on carbon 2, 2 on 3, 2 on 4, 2 on 5, 2 on 6. So that gives 4, 5, 6, 7, 8, 9, 10, 11, 12. And then a single oxygen. For compound B, there's again 6 carbons. Hydrogens, you have starting at the top, there's 3, 5, 7, 9, 12. So A and B look very different structurally, but they are isomers of each other. C, we have 1, 2, 3, 4, 5, 6. So again, C6. H, we have 1, 2, 3 on carbon 1, 4 on carbon 2, 5, 6 on carbon 3, 7, 8 on 4, 9, 10 on 5, 11 on 6, and then 12 is the OH. O. D is the exact same structure as C, except the orientation of one of the methyl bond up top has changed. And E is the last one. It ends up having C6H10O. So this is the odd one out. That's not an isomer of the other 4. Geometry of the nitrogen in methamphetamine. First of all, what's the hybridization of that nitrogen? It's got a lone pair. It's got 4 electron groups, 3 single bonds and a lone pair. That's right, that's sp3. So for sp3, what is the geometry? The electron group geometry is tetrahedral. The shape of the molecule would be trigonal pyramidal, C. 5. Which of the following alcohols will have the highest pKa? Highest pKa means weakest base. Sorry, weakest acid. So we have A, B, C, D, E. I'm seeing someone guess A. So that's right. If you look at all of these, they're the same compound. It's a carbon chain, 3 carbons with an OH on one end, with fluorines in various places. The strongest one by far is going to be E, because it has 2 fluorines very close to the OH, followed by then probably D, and then C is the next strongest, B is the next strongest, and A will be the weakest. The trick there maybe is making sure you realize that highest pKa means weakest acid. Here's the structure of morphine. Morphine's got an interesting structure with this weird kind of ring that you see. Which functional group is not present? So aromatic ring, I can see right here. Amine, I can see right there. Amide is not present. Remember, amide is a nitrogen attached to a carbon with a double bond. So amide is the correct one. Ether is present right here. Alcohol is present here and here. So the correct answer is C. Now we have an infrared spectrum. Which of the following molecules gives rise to the IR spectrum you see below? So remember what we're going to do. We're going to take a vertical line at 3000. I'm going to do my best without putting my hand on the screen. Hey, it worked that time. Maybe I can do better over here. It's not putting weird stuff everywhere this time. Okay, vertical line at 3000 and 1500. So over here, what we expect to see is sp3CHs. On the other side, we see sp2CHs. Look at this one right out here. What do you normally find at that point in the spectrum? It's where you find triple bonds, right? So that's either a C triple bond C or C triple bond N. This is all fingerprint region, which we don't worry about. You can see a little peak right here that it's small. It's between 16 and 1700 by the looks of it. It might be a CC. It's small though, so it's sort of on the borderline whether we worry about it or whether we ignore it. What we can do is start to go through our molecules here and start to cross ones out that don't fit. So you can see compound C is definitely not there because there's no OH peak right on this part of the spectrum around 3500. Also, there's no triple bond in that structure. The rest all have triple bonds, so that's good. But if you look at B and E, both of these have terminal alkynes. Terminal alkynes show a sharp peak out here for an sp hybridized CH. We don't see that, so we can cross off B and E as well. And then if you look, we're down to A and D. A and D are similar. They both have sp3CHs. They both have sp2CHs. They both have a carbon-carbon double bond, which we saw here, and both have a nitrile C triple bond N. So the difference is that D has that functional group, which is an ester, and A does not. Do we see the peaks we would expect to see for an ester here? Well, what do we expect to see for an ester? First thing we expect to see between 17 and 1800 is a very strong carbonyl peak. That was supposed to be a question mark. There is no carbonyl peak in this infrared spectrum, so we can confidently cross off D, leaving us with A. Fantastic. The sigma bond in propyne, indicated by the arrow below, results from the overlap of a what orbital on carbon 2 and a what orbital on carbon 3. So carbon 2 is sp hybridized, and carbon 3 is sp3 hybridized. So what happens for carbon 2 is the carbon, it has an sp that way and an sp that way. It's overlapping with one of the sp3 orbitals on the other side. We have hydrogens with their 1s. Remember, this one has a p orbital above and a p orbital in front and behind, and those overlap with sp and p on the final carbon on the left as well. But this bond here, that sigma bond, is an sp and an sp3, which is E. We're whipping through this midterm, especially because we can cross out ones like this that we didn't get to yet. For the following molecule, how many sp3 hybridized carbons are there? So right away, we can say that if a carbon has a double bond or a triple bond, it's not sp3. It's at least sp2. If it's triple bond, it's sp. So let's cross off all the ones that are part of a double bond. None of those carbons I kind of blanked out in blue, all of those are sp2, so none of those are sp3. How many other ones do we have? We have one here that's sp3, one here, and one here. So that answered D. Draw examples. I love this kind of question. And since I'm making midterms for you guys, remember that. I love making you guys draw things without giving you, with leaving it fairly open. Like a tertiary alcohol, you could do any tertiary alcohol you want. What you need is an alcohol where the carbon that the oxygen is attached to is bonded to 3 other carbons. So that's 1. So we need 2 other carbons here like this, something like that. An aromatic hydrocarbon. That's a hydrocarbon with an aromatic ring on it. A secondary carbocation. That's going to be a carbocation with 2 carbon groups attached. That we didn't cover yet. That we didn't cover yet either. And we're on to Lewis structures. Draw complete Lewis structures for the following. Show all lone pairs, formal charges, etc. First one is SO2. We're going to start out by just drawing the connectivity of these things. We're going to count up our valence electrons. So we have sulfur, and based on its position on the periodic table, we get 6 valence electrons. Oxygen will give us 6 times 2 is 12. That is a 6, not a 5, for a total of 18. We subtract 4 for the 2 single bonds we've already drawn, which is 14. And then we fill up the outer octets. So we get 2, 4, 6, 8, 10, 12. Leaves 2. Leftovers go on the central atom, like that. And we're done with this. Next, we would check to see that everything has a full octet. And very quickly, we would see that the sulfur does not. It only has 6 valence electrons and it needs 8. So we would look to an adjacent atom with a lone that might have a lone pair that we could pull down. And either oxygen we could use. We pull down the lone pair to make sulfur, oxygen. Next thing, now that everything has a full octet, is we would want to check formal charges. And the formal charges on the right-hand oxygen would be 6 minus the number of bonds minus the number of unshared electrons, which is 6, which is -1. So we put a minus there. And on the sulfur, we would say it's 6 and minus 3 bonds minus 2 electrons is +1. So we get a plus. Often when you have a plus beside a negative, you should ask yourself the question if you could take a second pair of electrons down and cancel out those charges. For example, can we bring that down there? If we did, we would make this. The nice thing about that structure is we've gotten rid of all our formal charges, which is fantastic. The negative about this, though, is that the central sulfur has exceeded its octet. That central one now has 5 pairs of electrons around it. It's got 10 valence electrons around the sulfur. It's got more than an octet. Is that okay? What do people think? Yes. It is okay, only sometimes though. It's okay if it's in row 3 or below. It's not okay if that was a nitrogen, for example, but it's okay because it's a sulfur. If it was oxygen, the same molecule, by the way, with 3 oxygens is called ozone. You can't draw this for ozone because you can't exceed the octet on an oxygen, but you can on a sulfur, so this is what we're going to go with. CH2O is the next one. So CH2O, we're going to use C as a central atom. O, H, H. If you add up valence electrons, we get carbon gives you 4. Hydrogens give you 2 because there's 2 and they're 1 each. Oxygen gives you 6 for a total of 12. Minus 6 for the ones we've already drawn leaves 6 valence electrons behind. And those 6 valence electrons we use to fill outer atoms. We'll start with the only outer atom that needs electrons. And that uses up all the electrons we have. Check for full octets. The central carbon does not have a full octet. So we can bring a pair of electrons down. And that gives you something that looks like that. Next, do formal charges. Believe me, all the formal charges on this work out to 0. Resonance structures. Draw the Lewis structure for the sulfate ion, SO4 2-, and 2 resonance structures for a total of 3 structures. I'm going to do this one, but I think before I do this, what I'd like to do is do a different resonance structure question, which is more like the ones we would typically ask you. And I'm going to jump out of that for a second and jump to this is the spring 2016. Both of these, by the way, are on Acorn under the old tests and exams. The other thing I posted up there a week ago or so were extra practice assignments for each unit. Those are something else you may want if you're looking for additional practice on this kind of stuff. This kind of question, where we give you a compound and ask you to draw resonance structures of it. We're asking you to push electrons around. And the main thing we have to think about is we have to make sure when we do push electrons around, we don't exceed any octets and we don't add or remove electrons from the structure. We're just changing their location. We're not taking them out or adding them into the structure. Normally what we do if it's a negative charge is we start at the negative charge and push electrons somewhere else. Or if we have a positive charge, we would like to push electrons towards it. So in the compound on the left, we have the sulfur with a minus charge and 3 pairs of electrons. So what we want to do is take electrons from the sulfur and push them somewhere else. So what I would think is if you take electron pair off the sulfur and say push it down there. So you can only push it into an adjacent bond. You can't push a pair of electrons all the way over to some other part of the molecule. You can only push it into a nearby bond. We could do that, except the electrons, that if that's all we did, then we would end up making 5 bonds to this carbon. So a pair of electrons that from that carbon also has to move somewhere else. So what we can actually do is take that pair of electrons and just push it up on the atom if we want. I don't know why this is not giving me dotted lines for some reason today. So what that did is it put a pair of electrons up on that carbon, and that carbon has a negative charge now. That's not a great structure because carbons typically don't like having negative charges. All these lines, by the way, they're not supposed to be dotted. They're supposed to be solid bonds. Can we continue moving them? Yeah, well, let's take this pair of electrons and push it into that bond and push those ones up onto the oxygen. That gives us our double bond to sulfur. double bond there, and oxygen. So those would be the three structures that we would be looking for. Of those three, which one do you think is best? A, B, or C? C, yeah. Good job, Lizzie. You wanted the negative charge on the most electronegative atom you can. So we can put it on a sulfur, a carbon, or an oxygen. Oxygen is the best choice there. Next one. We have a carbon here with a positive charge. It does not have a full octet. It has two hydrogens there that aren't shown. One thing to do if you are struggling with these that makes them a bit easier is if you go around and you draw in all of the hydrogens, it can help to prevent you from accidentally putting too many bonds to one atom. So what we're going to do is push electrons towards the positive charge. We would look for either a neighboring atom with a pair of a lone pair, or a neighboring atom that's making a double bond. So we don't have a neighboring atom, like the neighboring atom would be this one. It doesn't have any lone pairs, but it does have a double bond we could move. So you can move that over there. And if you do that, you make this. Another thing we could do is, say, take a pair of electrons and make a multiple bond there. Move this charge all the way around this molecule. That would put the charge here. And you get a structure like that. And you could continue doing this. You can move this all around this molecule. You could put the charge here. You put the charge here. What does this actually say? Draw two additional resonance structures. More than two may exist. Circle the most important, most stable structure for each of the molecule sets. You can show all hydrogens and carbons if desired. Draw curly arrows on the original structures and show the flow to make your resonance structures. Great. So there's actually another way you could have done the first one, which doesn't actually move the charge at all. Whenever you see an aromatic ring, what you can do is, if you want, you can just move the electrons around the ring. So we haven't touched the top half of the molecule at all here, but we've moved the electrons like that. That's totally okay too. That's fair game. Back to 2017. Do you guys want to see me draw resonance structures, or do you want to see me do other things? Sam, question.
Yeah, for that last one, what was the most stable structure? Did it matter?
The most stable structure is this one, for reasons that we didn't quite get to yet. So that's why
you're pointing at.
oh. Yeah, why isn't it coming up on my screen? I see it. The one is the one I drew under structure A, the first one I drew going down. Once my screen's just lagging behind me for some reason. My iPad's not behaving. The reason is that carbocations, they can be primary, secondary, or tertiary. So the best one is a tertiary carbocation, which is the one that I drew in structure A. But yeah, you don't have to worry about that right now. Okay, I'm going to have to unshare and share again. It seems to jog things every now and then. There we go. We're back. Okay. Do you want to do another resonance form? structure B, question B here, or keep going? I'm going to keep going. Didn't cover that. Formal charges. I'll just give you the answer. It's E. Comparing acid strength. We've seen a question like this kind of already. We're comparing a bunch of acids that all have resonance structures. The best structure here is going to be number 4, because it has 2 resonance structures and a fluorine nearby. Second strongest is going to be number 2, followed by 1, followed by 3 is worse than the others. 3 actually has resonance structures, but the problem with the resonance structures for 3, once you make the anion, is that one of those resonance forms looks like this. And you have a negative charge on a carbon. So you have a resonance contributor that's not a very good contributor, which makes it the worst of those 4 acids. IR. People love IR. I love IR. Okay. Vertical line 1600, vertical line 3000. Notice we have what looks to be a CO stretch and a CC stretch in this molecule. Looking at the choices down there below, all of them except E have the C double bond O, the carbonyl, except for E. So let's get rid of E right out. What about B and C? Those are carboxylic acids. What do carboxylic acids show? They show a great big band that looks like that, which we don't see in this spectrum. So B and C are out. We're down to A and D. The only difference between these two is A has a carbon-carbon double bond and D does not. But we see, right, a carbon-carbon double bond peak between 16 and 1700 reciprocal centimeters. That vertical line, by the way, is terrible. It should be more like, I don't know. That's not so good either, but it's better. The other thing is, if you look at this vertical line at 3000, we see there's absorption on the left and on the right. So we expect there to be sp3 CHs and maybe some sp2 CHs as well. And all of that points to structure A. The presence of the double bond, presence of the carbonyl. It is an ester, and ester often will show a strong peak in this part of the IR spectrum as well. But that's fingerprint, and we don't rely on that too heavily. Carbocation stability. So this comes back to your question, Sam, and we just covered this on one of the last slides. Which of the cations is most stable? And the answer is D, because it's tertiary. This is primary, this is secondary, and that's secondary. Question 5. Which of the following cation isomers receives the greatest amount of resonance stabilization? Which is most stable? What this basically means is which one of these has the most resonance structures? If you start drawing resonance structures, which one can you draw the most of for? Well, it's not B, because B you can't draw any resonance structures for, because that charge is isolated, we would say. Compound A, you could push electron pairs like that and put the charge there. You could put those ones over there and put the charge there, or you could put the electrons from this bond in and put the charge there as well. So this can share that charge over 4 atoms. It's got 4 different resonance structures. This only has one resonance structure, or one form, which is the one that's drawn. C, you could put the charge here by pushing those electrons over, and then you could push those ones over as well and put it there, giving you 3. This one is isolated. That double bond is isolated from the positive charge. D, we could put the charge here or here. There's 2. And E, you can put the charge here or here. You could draw a resonance form like that. This only has 2 as well. So clearly the best one here is A, because you can share it over the greatest number of carbons. Drawing isomers. It's a good one for you guys to try. We didn't get to that yet. I like question 9, which is drawing curly arrows to give the reaction that we see on the right. So I'm not even telling you what the reaction is. First one, maybe you can look at it and tell that it's an acid-base reaction. But what we're doing is we're going from a nitrogen with 3 bonds in a pair to nitrogen with 4 bonds. So it's made a bond to hydrogen. So we know there must be an arrow like that, starting at the lone pair of nitrogen, going to the hydrogen to form an NH bond. Cl goes from Cl with 3 lone pairs to Cl with 4 lone pairs and a negative charge. So the pair that's in that bond hops out and joins the chlorine to make chloride here on the right. The next structure, this one's a little more complex. This is a reaction we'll look at later on, chapter 5-ish, 6 maybe. The OH minus goes from 3 lone pairs to 2 lone pairs, and it's made a bond to hydrogen. So what happens there is that must have happened to make the water we see there. The chlorine became chloride again, just like last time. So we can pop that off just like before, but the carbons change to make a carbon-carbon double bond. So that pair of electrons in the CH bond here, those move between this carbon and this carbon to make a CC double bond. Okay. I think we're out of time. I know we're out of time. And I actually have to get to Oak Island. They want me there at 9:30, so I might be a few minutes late, but I'll be there very soon. What that does mean is I can't do office hours today, but I'm going to have extended office hours on Monday. So after our class on Monday, my plan is to have office hours starting immediately after class, going straight up until Terry's office hours start, which I think is 11. I might have that wrong, 11 or 11:30. So
Is
anytime
Monday Thanksgiving?
Oh, Monday's Thanksgiving. We don't have class Monday, do we? Maybe what I'll do, I'll send an email. Maybe what I might do is do an office hours thing Monday evening. Does that sound okay for people? It'll be online, and that way, if you have any questions before, I could do it Tuesday as well. I'll send an email. I'll make sure that you guys have access and that we can definitely meet if you have any questions. If you want to make a time, just send me an email as well, and I can meet with you kind of any time, except not today. All right, thanks, Lizzie. And you guys have a great morning, great weekend, and I'll see you guys soon. Stop the recording.